Welcome back. So we have a cubic here again. This one is y equals x cubed minus 12px plus r. And so p and r are just numbers, they're constants. So if we change those constants, we would change the shape of the cubic. So if you have no intuition about this, definitely check out Desmos or use your graphics calculator and just plug in a few values and see what happens. But here they're telling us that the lengths of these orange lines and the central blue line will change. Right, so B and C, they are sort of corresponding to the max and the min, and then that blue line is the point of inflection or the point of rotational symmetry, so kind of like the center, it seems like. They've given us a few examples. And for some combination of P and R, the curve can intersect the x-axis 3 times. This will happen if each orange line is longer than the blue line. Now we need to find the exact values or the condition for P and R for it to have 3 distinct x-intercepts. All right. So where to start? We're given the x values of B and C. Let's just have a think. If this orange line was, I don't know, let's say here, and this orange line was here, and the blue line was the same, right? So it goes through that point. We would have a cubic that looks like that. So that is only one x. Well, is it an x-intercept? No. Well, one down here. So for there to be 3 x-intercept, we would need this orange line at C to push all the way down here, below the blue line. And I mean, this one would do the same. And we'd be left with a cubic like so. So the condition to have 3 distinct x-intercept is length of orange line must be greater than length of the blue line. Right? If it's less, like is the case in this picture, we just have 1 intercept. If it was equal, we'd actually have 3 intercepts, however 2 of them would be the same, right? They're just touching the x-axis. So this orange line must be greater than the blue line. All right, that was the hard bit, working that bit out. Now we just need to actually get the length as a function of x, right? Or as a function of p, rather. So looking back up at our original function, plus r, that would actually be this line here, right? This dotted line, that's the y-intercept, which is the length of the blue line. So we know the length of the blue line is just this height, which is the y-intercept, which is when x equals 0, which in this case is r. Now the length of the orange line is this height, take away r. Right, so the y value of b, which will give us this height, taking away this smaller height r. So let's get that height there. So the y value of b, well, we know the x value, and we can substitute that into the function, and for x, to get the y value. So y equals x, where x is negative 2 times p to the 0.5 cubed, minus 12 times p times x, where x is negative 2 times p to the 0.5, plus r. And let's simplify that. So negative 2 cubed, what's that? 8? No, negative 2 times negative 2 is positive 4 times negative 2, negative 8. P to the 1.5. Now we have minus 12 times minus 2, so plus 24. And then p times p to the 0.5 is another p to the 1.5. Right, multiplying powers, we add them together, plus r. Grouping like terms, minus 8 plus 24 is 16p to the 1.5 plus r. So this height here is 16p to the 1.5 plus r, which means the length of the orange line is that expression minus r, which would just give us 16p to the 1.5. So, for there to be 3 distinct x-intercepts, this inequality relating p and r must be true. Now let's see where we stand on this question. So we just said 16p to the 1.5 must be greater than r. Now it's asking us write it in a form where the exponents of p and r are both positive integers. Well, integer meaning a whole number. Right now we have a fractional power, so that's no good. What we can do is instead of writing 1.5, we could write 3/2, right? Still not an integer, but when it's in this form, we can then express it in surd form. So that's where it's p to the power of 3, but it's square rooted, right? That's where the 2 is in the denominator, so it's square rooted. Must be greater than r. What next? We could divide both sides by 16. And finally, we could square both sides, right? So that would eliminate the square root. So p to the power of 3 equals r over 16 all squared. And so we have an inequality, right, or a condition relating p and r. The exponents are positive and they're integers, right, 3 and 2. Again, just to summarize this one, because that was a lot. We're given a particular type of cubic, and the constants p and r actually adjust the lengths of the orange lines as well as the blue line, right, the y-intercept. And to get 3 distinct x-intercepts, we worked out that the orange line must be at least greater than, so it must be greater than the blue line. From that, we found equations for the length, and then we just put that in our inequality and then rearranged to answer the question.